Okay, example number 2 is radioactive decay. The radioactive element, bismuth 210, decays into polonium 210 with a half-life of 5 days. This is actually true. So I picked a real example with a very short half-life, 5 days. We can find the equation for the quantity of bismuth 210 as a function of time this way. So what do? We use this formula, A of t equals A naught, that's A sub 0, capital A sub 0, times little a to the t power. So capital A of 5, putting in the information, equals A naught A to the 5, A to the 5th power. Now they want to know, they give you that the half-life is 5 days. So we put in the 5 for the half-life. What should A of 5 be? A of 5 should be half of the initial amount. So A sub 0 should be half of A sub 0. So I should replace A of 5 with A sub 0 over 2, which I did there. Now notice that, first of all, if A sub 0 is 0, then you started with no bismuth 210, and of course you'll end up with no bismuth 210. So we can, that's not interesting, we can ignore that case, so we can assume that A sub 0 is not 0, does not have the value of 0. And that means that we can divide both sides by A sub naught. Okay? A sub 0. Naught, that's N-A-U-G-H-T, it means 0, A naught. Okay, so this is 5 days for the quantity A naught to be reduced to A naught over 2. So assuming we are starting with some bismuth, 210, so the A naught is not 0. I kind of said this already. We get, okay, then we get this. We can divide by the A naught on both sides, and we get A to the 5th equals 1/2. Then to solve this, we take the 5th root of 1/2, which I wrote as 0.5, just because it's easier to enter in a calculator that way. In fact, I actually did it as 0.5 to the 0.2. The 5th root is the 1/5 power, which is a 0.2 power. So that's what I did. That's what I did here. But you could enter it this way if you have a calculator where you can put in the 5 there. If you don't, then just do it this way. And I estimated it to 5 decimal places. Because if they don't tell you, that's usually a good, for most of the stuff we do, that's a good number of digits to estimate it to, if you're going to use it in another computation. So putting that into the original equation here, right, we get A sub t equals A naught times, our little a is 0.87055 raised to the t power. I put that in parentheses mostly because of the decimal point. It just makes me more comfortable to have that in parentheses. It's not really necessary there, but I put it there anyway. Where the time is in days. Why is the time in days? Because the half-life is given in days, 5 days. Okay. So if we start with 0.5 grams of bismuth 210, how much remains after 21 days. Well, you just put the numbers in, right? Because you already figured out what the base of this exponent is, which is the rate of decay. So a sub 21 equals 0.5 times 0.87055 raised to the 21 power. That's why I kept so many decimal places. I maybe should have kept more. 21st power is pretty high, which is approximately 0.027 grams. I rounded it off to 3 decimal places. The problem should have said how many places to round it off to, obviously. And it will when you do problems, it'll say how many to round it off to. But always keep, when you're still computing, if you're going to round something off, leave a few extra digits so that you don't get too much error in your problem, and then round it off at the end. Don't round it off to 3 digits the first chance you get. Like this base here, don't round it off to 3 digits. Because when you do this, the error is going to be compounded. In fact, you might just want to take this number, stick it in a memory. If you don't know how to do that, Google it for your calculator. Stick it in a memory, and then when you type this out, just put whatever letter you use for the memory, put that right there, and raise it to 21. That way you'll have like 24 digits or something in there, and you'll be sure to be accurate enough.